Okay, the video here is covering Chapter 17, Sensitivity Analysis, the Greeks. It's a basic interpretation. I'll follow this up with another video that gives you more insight and intuition. The example I have will cover a stock with a price of 25, a strike of 23, time to maturity of a half a year, 35% volatility, risk-free rate of 1%. The call price is $3.56. The put price is $1.45. And then we have all of the Greeks down here. The first one is delta. You notice the delta is positive for the call, which makes sense because we know that when the stock goes up, the call goes up in value. Also, with a put, it's negative because when a stock goes up, the put goes down in value. Gamma, which measures curvature, is 0.0574, and it's equal. It's positive. Curvature is always positive. It's equal for the put and the call. Theta, which measures time decay, see the negative there, reflects what happens when you increase time. In a sense, time to maturity declines. Your option decays in value, and that's captured by theta. Vega measures the change in volatility and how that affects option prices, and notice that it's equal for both calls and puts. And then Rho covers how does the value of the option change with respect to a change in interest rates, and it's positive for a call, negative for a put. That is consistent with what we saw in the pluses and minuses table that we covered at the end of one of the early chapters in options, where I said basically, look, with respect to a call, we know that a call represents a substitute for buying a stock. So if you're long, in other words, you want an underlying asset to go up, then you can either buy a call or buy a stock. Well, if you buy a stock, you got to shell out a lot of money for the stock a stock. The call is usually much cheaper. So in terms of opportunity cost of money, it's cheaper to buy the call. And so when interest rates go up, calls become more valuable because it takes less money to buy them. Now, with respect to a put, keep in mind that a put is a substitute for shorting a stock. And if you short a stock, your broker will sell the shares for you, put the proceeds in an account, and that will earn an interest rate. And if interest rates go up, now that shorted stock is relatively more valuable than buying and actually shelling out money to buy a put. Therefore, when interest rates go up, puts are less attractive and the price goes down. So now what I want to do is give you an interpretation of how these work. And so the first one we'll do is delta. Okay. Delta is the change in the call for a delta times change in S. And so our delta, according to the previous table, was 0.685 times $1. Let's make a dollar change. Technically, delta only covers a small change, and it's a linear change, as we'll see in a few minutes. And a dollar is not a small infinitesimal change, but it's a nice unit to change, so you can wrap your head around the interpretation a little better. And so in this case, we got about for if the stock goes up $1, what we're saying is the call will change in price up about 69 cents. Okay. Now the next one, Greek, is gamma. Gamma measures curvature, and it's the change in delta. For any of you who are familiar with calculus, it's the second derivative, and you know second derivatives measure curvature. The first derivative, which is basically delta, looks at the slope at a particular point, and gamma will pick up the curvature part of it. Now, the change in delta equals gamma times a change in S. Okay. And if we look at the table, we see that we have a 0.0574 for gamma times $1 change in stock price. We get about 0.0574 is the change in delta. Now don't try to put a dollar sign here because it's the change in delta. Basically delta would be going from 0.685 that we just used a minute ago here and increase it by 0.0574. That's basically what we're saying. Look, this delta will go up by 0.0574. Okay. Now, it's helpful, and you'll get some insight with delta gamma effects. Okay. And so what I'm saying is, let's look at the change in the call for a change in delta times the change, I'm messing this up, change in S. Okay, so here's the delta effect. Now we want to measure the curvature effect, and the curvature is 1/2 gamma times the change in S squared. Okay. So this is the 0.685 times $1, 69 cents like we saw, 1/2 times 0.0574 times $1, okay, because squared. This comes out to be a little over 71 cents. And so what we have is, if we take into consideration the linear change through delta and curvature, we will get we'll capture most of the change in the option price. And I say that because what I did was I verified it. I said, look, you know, the call is 356 according to the table I showed you when the stock was at 25. Now, if we change the stock to 26, so it goes up $1 like I've said here, what happens to the call? Well, the call turns out to be $4.28. The difference is 72 cents. So we're pretty darn close. And you know, I got a lot of rounding here, so we'll be close. It won't be exact because there's additional curvature beyond taking a second derivative, so to speak, and gamma. So there's third and fourth levels, but they're basically immaterial, especially for our purposes. Next one is theta. So let's look at theta here. And that's the change in the call for theta times a change in time. And so the theta that we were looking at on the table was negative 0.2334, and I'm assuming, now look right here, I'm going to take a nice clean unit of time, and that's one trading day. So 1 out of 252 trading days. And the reason for I'm using for 252 is it accounts for holidays and weekends. So I'm not counting those in there. I'm looking at active trading days. And so there's controversy in the literature on how to calculate this, because you can think of it as okay, the only time the option price actually changes is when it gets recorded on an exchange, and the exchanges are only open Monday, Tuesday, Wednesday, Thursday, Friday, and excluding holidays. So this would make sense, 252 trading days. But in theory, even though the option is not trading on a Saturday or Sunday, it's still decaying in time theoretically. So keep that in mind. It's controversial. But I'll follow with the literature. Most of the literature will use the number of trading days, so I'll be consistent there. And so what we're saying here is that we're basically going to have, as you march through 1 day of time for this option, you're going to lose about 9/10 of a cent, almost 1 cent, because of the in 1 day, because of this. And as you get closer and closer to expiration, you'll find that theta will I was going to say increase, but be careful, it's a negative sign. It actually gets more negative, which means time decay is even a bigger factor. Okay, and we'll see that when I cover the intuition in the next video. I'll show you that a little more in depth because it's worth knowing. Okay, the next Greek is Vega, actually not a Greek. And Vega here is we're looking at the change in the call for Vega times the change in volatility. And Vega was 6.28 positive times 0.01 for the change in sigma. And that was going from 35 to 36% is what I increased it. So that's what I'm thinking here when I'm looking at the change in sigma. And that is, 0.0628 positive. And what that's saying is that's basically about 6 cents. So if the volatility during the life of the option increases by 1%, you're going to have an increase of 6 cents in the options Vega. In the change in the call price. It's going to go up by 6 cents. Okay. Now, let's look at the last one, and that's Rho. So we're looking at the change in call again, equals Rho times the change in R. And Rho, according to our table, is 0.76. Change in R is going to be 0.01, so I'm going from the 1% to 2% that I used to compute this Rho. And what will happen is we'll get about 0.0678, or about a 7-cent increase if interest rates go up. So if interest rates double from 1 to 2%, we'll get about a 7-cent increase in the option value. Okay. So now what we want to do is we want to look at how each of these Greeks changes with respect to moneyness, and how these Greeks themselves change over time. And so we want to get some more intuition on what drives these parameters.